Hello everyone, welcome to the design of roof truss. This is in continuation of the first video about wind loads and dead loads design of roof truss. The structural member that we designed first in this video is the Purlin. During the first video we calculated all the loads. The loads calculations are all in the first video before this. The wind loads and live loads design of roof truss. So here are the picture again from the first video. Purlin size is 2 by 3 with 0.7 meter on center with 2 by 2 wood plate right here, and I use gauge 28 GI corrugated roofing. The rafters are 2 by 6 and space is 1.2 meter on center. Again, this illustration of the tributary area. If you want to see the calculations of all the loads, the final loads for the Purlin, you have to go back to the first video. This video now is to solve for the shear moment diagram to get the maximum moment and maximum shear for the Purlin to be designed. Alright, now here's the Purlin is carrying 2.575 kilonewton per meter load. Is a uniformly distributed load along the entire length of the Purlin. The Purlin is carried by 4 rafters. Okay, there are more rafters in there, but this is the commercial size of. You gotta go by the commercial size of the wood, which is 3.6 meter. That's the length of one rafter, and could be overlapping. So we get design one length of rafter and then apply to all the rafters whatever size we can get from our design. So the rafters will have the 4 reactions right here. The reactions transferred to the rafters, the 2 interior and 2 exterior rafters. In structural analysis representing 2 or 3 dimensional objects like this one here, there are 2 or 3 dimensional objects into one line is called idealization. Okay, and the total load of the Purlin is 2.575 multiplied by the length of the Purlin is equal to 9.27 kilonewton. That's the magnitude, the total load. See, there are 4 reactions here. I'm gonna show you why we're not going to use the moment distribution to solve for the maximum moment and shear due to the load. Here's the moment distribution table. The reason why it is called the moment distribution is when there is an unbalanced moment between the 2 spans right here at the joint, like see B here. If there is an unbalanced moment here, it goes here. Alright, and since there's nothing to balance here, the balance is 0. If you add these 2 here, negative positive is equal to 0. Same thing with the joint C. So there is nothing to distribute here. The moment distribution is mainly used when the joint of your frame has an unbalanced moment. And since this is very symmetrical load all the way, the result, they have the same moments at both ends, all of them. See that? AB moment, positive, negative, 3.09, all of them are the same. And you put it together in a frame like this one here, the balance there is 0. So therefore, we're not going to use the moment distribution. All we can do is approximate method, which is more applicable in this type of loading. Okay, now here's the loaded Purlin. In every midspan of the Purlin, right here between these two reactions and these reactions, in between at the midspan, you have to install the hinge. When there is a hinge installed, that is the point where the considered to have a 0 moment. Therefore, that's the point where we can divide the Purlin. And when you break any structural member, it has two forces there, the shear force, and it is represented with two arrows, one going upward and one going downward. That's the presentation of the shear force, and the value of the shear there, each of them, they are the same shear because it's in the cut in the midspan. You have to cut the beam right here, or we have to cut the Purlin right here. So the value for the shear is half and half, they're the same. So it's the load, the uniformly distributed load multiplied by is 0.6, which is the half of the 1.2, and that is the 1.545 kilonewton, and same as this half here. And obviously by inspection you can, this is very symmetrical loading, so you can see that the reaction here at C is obviously the load carried this area here, which is the magnitude of that load there is 1.2. This is the span. Okay, half and half is carried by this rafter C. So it's 1.2 multiplied by the uniform distributed load. It gives you 3.09 kilonewton, and equally the same as the interior rafters. These are the rafters in blue. This is the structure that carried the Purlin. Alright, Purlin is sitting on the rafters. See as the other interior rafter is 0.09 kilonewton, and the exterior rafters carry half only of the beam, half of the Purlin, which is 2.575 multiplied by 0.6. You get that they are the same. So all the reactions are right there now. That's the reaction carried by, that's the load carried by the rafters. Now since we have all the reactions, let's check if the reactions is equal to the load. The downward load is supposed to be equal to the upward load, so we can make sure that all these reactions we have are correct. So checking that, using the condition of the equilibrium of summation of vertical forces is equal to 0, RA plus RC plus RE plus RG is equal to 9.27 kilonewton, and you solve this together, you calculate this is 9.27, this is the upward, and equal to the downward, which is 9.27 as well. So therefore all these reactions we have are correct. Now since we have all the reactions, let's go to the shear moment diagram. Solve for shear moment. So here are all the reactions here. They're going upward. Now let's start solving for the shear A. The shear at A here is the reaction at A, which is 1.545. So from zero line of shear, this is the shear line. This is the division between the positive and the negative shear values. Okay, to draw the line of the shear for A is from 0, and then you calibrate this line here, locate the 1.545. You know, it could be there, it could be here, but I calibrated it right here. That is the location of 1.545 for this load here. So therefore, you draw that line from here, from 0 to A. That line there, you draw that line from here up to there. Now, to solve the shear for B right here, the shear at B here is the calculation as well. It's the shear from A. You always look at the load, you know, when you on the process of solving shear. From the beginning, you look carefully. Okay, what's the next load? The next load is this magnitude of this load here, the uniformly distributed load, and you calculate this uniformly distributed load is 2.575 times the span. You have to stop every load. Okay, this is the load that we are going to solve now, and stop it right there. So we only need this to calculate the B. Alright, the shear B. So it's minus 0.09 kilonewton. All of these loads are the same. Minus 0.09 kilonewton. So to solve for the shear of B right here, shear at B is the shear A, which is positive 1.545, and minus that is an upward. This is positive, and this is going downward 3.09. So positive 1.545 plus negative 3.09. That's how you solve it. You use plus, and then consider the sign. You have to mention the plus, and then plus the negative 3.09. You get to add two numbers having a like sign, you take the difference and obtain the sign of the greater number. So the sign of greater number here is negative, therefore B here is negative 1.545. So right there. So we have the value there. Again, you calibrate this, the line, shear line, vertical shear line. There's horizontal and vertical shear line. So we calibrate there, so it's almost equal to that one there, so it's right here. You locate that line there, the point, and then from A going to shear B, you draw this line here. You draw that line from A to B. There we go. So you have the negative 1.545 kilonewton. Now solve for shear at C. Okay, the shear at C is the B, the shear at B, and plus the shear, okay, what's the load at C? There's a reaction load here. It's just going upward, so that is positive. All the upward loads are positive. Alright, so to do this, the shear at C is by saying this: negative 1.545 plus positive 3.09. You get, again, retain the sign with greater number, which is positive. You get positive 1.545 kilonewton. Now locate that on the vertical line, so it's almost same as location right there, so I locate it right here. And then from B, now you're at C. From B here, since this is concentrated load going upward, you just draw a vertical line from B to C. So that's how you do it. Draw that line, See the blue there? That's from one end to the other end. Draw the vertical line there to C. Now solve for the shear at D. Okay, the shear at D again. Always go back to real. It is continuous, right? Okay, think about that line is continuous. So we have continuous Purlin. So when you go to the next point, you have to consider the last one where you left off. Alright, so the shear at B here is the shear at C, which is positive right here, and then the negative, and along this area here you have to stop. There's a reaction there, so all we need is the load here. We're done with that. We are here at C, and then we're going to the D, right? So we need this load here. This load is minus 3.09 as well. If you multiply 2.575 multiply by 1.2, you get that. All of it at C. So the shear D is this shear here at C, which is 1.545 positive plus the negative minus 3.09. Again, retain the sign of the greater number, so we get negative here. So it's a minus 1.545 kilonewton. And locate again that location of 1.545 along the vertical line. So locate that, it's right here. And then after locating that, you draw that line, you connect that line from where you left off, which is C. Now draw the line from C to D, this line here. Draw that line all the way to D. Alright. There you go, same thing at E, shear at E. So we're done with this load here, we're done with this load here. Now we're going to the shear at E. The shear at E, there's, look, this is the reaction here, which is 3.09 positive going upward. So therefore the shear at E is the shear from D. Always go back and look at behind you. The D. So D now is minus. Okay, so negative 1.545 plus the positive, it's going upward, 3.09. Greater number is 3, so we get positive right here. We take the difference because it's an unlike sign. So we got positive 1.545 kilonewton. So that is the shear at E. Now since this is a vertical force right here, the reaction, we're not going to do inclined line, we're going to do the vertical line. So from D, alright, so you locate that along the vertical line, the value of 1.545, and it's positive, therefore it's above the shear line. This is the shear line here, and that's the shear line. Above that is positive, so right here, this location. So from D, you're going to E now, right? You draw that line going to E. Draw this line here. That blue points there, up to here. Alright, now you're at E. Going forward, now you're going to F. The next is F. The shear at F is the shear at E, which is positive. The same thing, 1.545, and then, and since there's a load here, the reaction here, you have to stop there. Okay, so we all need this load and calculate against this load here. Alright, so shear at F is positive 1.545, which is the E, and that is positive, and plus the negative 3.09. the load, the uniformly distributed load is going down and crush this 1.545. The result is you have to carry the negative sign, which is negative, has the greater value. So shear at F right here is minus 1.545. Alright, now again locate from this vertical line the location of 1.545. Locating it is right here, and then after locating that, you draw the line from where you left off, which is E. From E you connect that line there up to here. This line here you have to draw from E to F. Now you're there. One more. Now the shear at G. Same thing. The shear at G is the shear at F, which is minus 1.545, and since this is vertical going upward, that's positive, so minus 1. The shear at G right here is this is the minus and this is the plus. So you calculate that, the plus 1.545 minus 1.545, the shear at G finally is equal to 0. It should be 0. Okay, at the end here, the end of the Purlin, the shear here should be 0 and the moment here should be 0, so that all the calculations are correct. So we have that, everything 0 at G right here. The shear there is 0, so therefore all these values are correct. Alright, now let's go to the moment. Okay, to solve for the moment you need an area. So solving all the areas here, area 1, that's area 2, area 3, area 4, area 5, area 6. The area of that is the area of the triangle, which is 1/2 base times height. The base here is the span, the length, horizontal length, and the vertical is the height. Okay, and the vertical value is the value of the shear. Alright, so that's shear there. So area 1 is equal to X, is the base, times the shear, the height, 1.545 kilonewton over 2. So the area of a triangle. So we don't know X. We don't know if it's, because it's passing through the intersection of the 0 line. So we have to calculate the X. We don't know the value that to make sure what is that there. What is this? The dimension of this X here. So to solve the X right here, so for X we have to use the similar triangle, the big triangle, and put the small triangle in the middle. The large triangle is the summation of this shear here. You add this to the shear over here. That's, you put it together like this one here, like that, and then draw a line. Then the small triangles in the middle. So add these two shears here. Forget the sign. That's not where we are. Here we're looking for the height. The total height of that is multiply 1.545 times 2 equal to 3.09. So that's the height of the triangle, the large triangle, and the middle is in the small triangle, and the horizontal distance for that large triangle is 1.2. Alright, so 1.2 here horizontal, and the small triangle now is 1. We're solving for X, okay? By similar triangle we can do that. It's 1.545. You draw the triangle here up to there, and this is an X, the distance X. So to To solve for x, you have to equate both triangles. The small triangle is equal to the large triangle. And when you do that, you always start with the horizontal distance, okay? As the numerator and the denominator is the height. Okay, the vertical. Horizontal divided by the vertical. So x, the horizontal line for small triangle is x, and divided by 1.545 is the vertical line right here, and equate that to the large triangle, which is 1.2 horizontal divided by the vertical, which is 0.09, and then you have this equation here. And to solve for x, you have to cross multiply this equation. Okay, this value here goes here, and the 3.09 remain the same, so we have it here. Solving this, you get x equals to 0.6, which is really symmetrical. And I'm just showing you how to do that whenever you encounter unsymmetrical loading. So it's by similar triangle you can solve the value of x, the distance x. So now we have the x. Area 1 is 1/2 base times height is equal to 1/2. X here is 0.6. You gotta put that there. We put the 0.6 there. Is equal to the area of that area 1 is 0.464. That's a kilonewton meter. And the area 2, the same thing, is the, since this is 1.2 minus x, this is also 0.6. Alright, so area of 2 is 1/2 base times height is equal to 1/2 0.6 times 1.545 is equal to minus. This is now, this is a negative. Okay, this is minus. Since this negative is minus 0.464, and in the area 3 the same, they have all the same areas. So this is positive, this is negative 4, and area 5 positive, area 6 is negative. They are all the same values. Alright, area. Now solve for the moment. So you know how to get the area. Anything below the line of the shear is negative, and above they're all positive. 135 positive and 246 negative. Okay, so now solve for moment. Moment at B, which is moment 1 right here. This is the calculation. Moment 1 is the area 1, which is this one here. The area 1, the area of this, becomes the moment right here, which is 0.464 kilonewton meter. So moment 1, which is moment B, is 0.464, and the moment at C right here, which is moment 2, is the moment here that is positive, right, minus the negative moment of moment 2. The area 2 is the moment of, which is the moment 2. So area moment 1 minus moment 2 is right here. So moment 2 is equal to area 1 minus area 2 is equal to 0.464 minus 0.464 is equal to 0. So moment here, let's see, is 0. Now the moment at 3 is the area of 3, which is positive, so it's, the curve is going above. So locate that 0.464 is positive, so it's above the line, 0 line of the moment, so it's right there. And then from there you draw a 0 degree, second degree, this, first degree. This is the second degree line. The inclined line is the first degree line, and the horizontal line is the 0 degree line. So second degree line. This is the first degree line, and this is the